In ChemTalk 5, we will discuss the orbit and orbital. Today's talk comprises Introduction, Atom and Orbit, Atomic orbital shapes of orbital, s orbital, d orbital. An atom is the smallest component of an element that can retain all of the chemical properties of that element. All atoms contain a small, dense nucleus consisting of protons and neutrons surrounded by electrons moving in a specific region, energy level called an orbit or shell. These energy levels vary since the orbits closer to the nucleus are lower in energy, while the farthest ones have higher energy. Protons and neutrons reside inside the core of the atom. Proton is a positively charged particle that has a mass of 1 and a charge of +1. However, an electron is a negatively charged particle that travels in the space around the nucleus. In other words, it resides outside of the nucleus. It has a negligible mass and has a charge of -1. Neutrons, like protons, reside in the nucleus of an atom and have a mass of 1 with no charge. Since an atomic orbital represents the space around the nucleus in an atom where the electron spends most of its time, while in constant motion, therefore can be defined as the three-dimensional region or space. It means volume, around the nucleus of an atom where there is a maximum probability of finding an electron having a certain amount of energy is 90 to 95%, and is called an atomic orbital. Since the atomic orbitals are mathematical functions, they provide insight into the wave nature of electrons that exist around the nuclei of an atom. In quantum mechanics, the mathematical functions are employed to determine the probability of finding the electron in a specified region. To clarify the concept of electrons' probability, let us assume we take a set of instantaneous pictures of an electron with a specific energy moving around a nucleus, with the electron appearing as a small dot in each picture, was superimposed them upon each other. A cloud would result as an electron density representation. Thus, the density of dots in a given region is a pictorial representation of the probability density in that region. The characteristic shape of each atomic orbital is dependent upon the values of the quantum numbers, such as the principal quantum number, azimuthal quantum number, and magnetic quantum number. However, the salient features regarding their shapes are as follows: s orbital. All s orbitals are spherically symmetrical. The effective size of s orbitals increases as n increases, principal quantum number. Each s orbital has regions of high electron density, shown as spherical shells. Between the spherical s shells, there are nodes with zero probability of electron density. P orbital. There are 3 p orbitals, designated as px, py, and pz, oriented along 3 axes, viz. x, y, and z axes are perpendicular to each other. The 3 p orbitals are also perpendicular to each other. All 3 p orbitals, namely px, py and pz, have dumbbell shapes. Each of the 3 p orbitals has 2 dumbbell-shaped lobes that touch each other at the origin, i.e., nucleus with minimum electron density. The p orbitals are disposed symmetrically along one of the 3 axes, called orbital axes. This means that the 2 lobes of each of the 3 p orbitals extend outwards and away from the nucleus along the axis. The major lobes are separated by the nodal plane, an area with low electron density denoted by a red circle between the lobes in the diagram. Thus, unlike s orbitals, which are spherically symmetrical, p orbitals have directional character, which determines the geometry and properties of the molecules. However, the positive and negative sign on lobes are lobe signs, not the charges. Although all the p orbitals of all the energy levels have similar shapes, however, with the increase of the principal quantum number, denoted by n, of a shell or orbit, their size increases. Was this helpful? Please like, subscribe, comment, recommend, and follow me for more such talks.